slides describing his part of a project. So it's really different aspects of trying to tackle the beginnings really of a project. So it's not really correct, Marcus and Kalle, that we have accomplished great things. What we have accomplished is to start research, but we haven't published anything yet. So what you see now will be unpublished data, which I hope will stay such until me and Richardson can write it up and publish it properly. Okay, so this is probably a redundant slide for you guys who have seen, you have been wise enough to join UPV, right? So you know some of this already, the renaissance of psychedelics. But I would like to put it into numbers from a more academic perspective. Here you see publications per year and LSD, psilocybin, mescaline. I think it's interesting to see that mescaline started a few years before the others. Actually, the line should extend further in this direction, because before PubMed was really fully operational, of course. They haven't logged so many of those early articles. The first article, I believe, was in the early 1900s when mescaline was synthesized. But this perspective, I think it's interesting to take from a not only popular science perspective, but also a bit more academic, in the sense that mescaline was the first compound that was studied by the scientific community as a psychotomimetic. That is, taking it gave the subject quite a few of the characteristics of psychosis or schizophrenia, being quite similar, not identical, but similar. And this model, schizophrenia model or psychotomimetic model, was studied with a small number of publications in the early 1900s. When Albert Hofmann synthesized LSD and Sandoz decided to distribute that, everything took off onto a different level, as can be seen here in the PubMed publications in the 50s and especially the 60s. Intense clinical research on many indications, but also increasingly a non-clinical use in US, not so much in Europe, but in the US a lot, which led to long story short, which you know, but psychotropics, as they are called legally, that is, psychedelics, were banned in a UN treaty. So all member countries have to enforce that, and it's interpreted in slightly different ways, but essentially all these classical psychedelics are illegal. Now, the Renaissance, everything took off, one could say clinically at least, with Strassman studying DMT in '96. And there is still some debate whether this is endogenous. There are many studies showing that it is produced in our brains right now. But there is also some doubts about the levels, if they can DMT actually does something in the brain, and if so, what? A lot of question marks about DMT. So I think it makes more sense what Johns Hopkins did in early 2000 to study rather poor patients, poor in the sense that they were dying from cancer, and see if psilocybin could do anything to alleviate their pain and their depression. And really impressive results led to this field clinical starting to bloom. And this study in 2016 was, I think, an icebreaker, because suddenly we could show that treatment-resistant depression was apparently treatable with psilocybin. And now in 2020, last autumn, we were very happy to see that we got approval from the first study with psilocybin in Sweden, currently being run with the first patients at Karolinska Institute. Okay, history. Now, perspective. I promised a bit more scientific perspective on this. And me being a medicinal chemist, I have to show you structures. This is what we do as chemists. And this is a language more than anything else, a language of structures instead of characters. And I think most of you know enough to see that all these can be produced by nature or a lab, and it wouldn't really matter. That's at least the scientific standpoint of things has been for over 100 years, that it doesn't really matter. But this slide is now on synthetic analogs, and the next slide with psychedelics is mostly natural ones. Natural in the sense that they're produced by cacti or animals or mushrooms. But let me go through these first. The perspective that antidepressants that are being prescribed massively today, massively meaning more than 10% of Swedes today are using antidepressants. And the vast majority of those who use antidepressants today have been doing so for many years. This is a treatment that was developed to be given short term, a few months, and now it's been given for 10 years and is really difficult to terminate, to stop taking. They do help some, and so it's really useful medications, but they don't really treat the cause of depression. They treat symptoms, which is a perfect match with the pharmaceutical industry business model. Sell a pill every day to many patients. It's great. Antipsychotics, these are much more brutal compounds. This is Haldol, and I don't think you would want to have that. It's more of a compound that is there for the personnel at clinics with severely disturbed patients. If you give Haldols to someone, they become very calm, even though they don't necessarily feel calm on the inside. They appear calm on the outside, but it's easier to handle. So some rather nasty compounds here for the user, but still used extensively in the psychiatric care. Then you have the more anxiolytics and sedatives. If you want to go to sleep or have a lot of anxiety, you can use benzodiazepines or zolpidem. You also have stimulants being widely prescribed for all the initially children with ADHD, but also a lot of adults today. And then mood stabilizers for those with bipolar disorders. So there's quite a bit of toolbox that we have today, and yet psychiatrists, no one I've been speaking to of a psychiatrist are really happy with this toolbox, because what it does is to some extent alleviate symptoms, but these don't offer a cure really. Some actually harm the patients quite extensively also, especially some of the mood stabilizers and antipsychotics. It's a balance really. What is interesting with this perspective also is that the antidepressants, there is this story being told that it's serotonin stabilizing, and that you have, it's not, the depression is not necessarily a psychological disease, it's a signaling substance imbalance in your brain, and that can be corrected with these compounds. And that story doesn't really hold. I could talk for quite some time about that, but the evidence that has been revealed the last decades really show that it can't really be the case that you just normalize serotonin levels with this. They do work to alleviate depression, yes, but it's not the way that it's described in media. Interesting also was that without this model, the schizophrenia model that was studied with mescaline, with LSD and psilocybin decades earlier, it would not have been possible to invent those serotonin signaling substances, the antidepressants, now being used by 10% of the population. So we can thank psychedelics for all these drugs, not all of them, but many of them at least. Moving over to psychedelics now. I'm sure you know most of these. I grouped them into classical psychedelics, defined as being active at the 5-HT2A receptor. And you have a well-known mescaline, LSD, which it's from ergot, so it is partly synthetic, but this main part of the structure is really a natural product. And then you have ayahuasca, the combination of DMT and harmine, various herbs from the Amazon. You have psilocybin from fungi. And the most recent addition to this natural psychedelic was this 5-methoxy DMT, the toad, that was actually just realized in the 50s, that 1950s, that this was potent, a psychedelic that can be vaporized. And these guys, serotonin A and ibogaine, are very different, still natural, but working on different receptors. And these synthetic dissociatives are different in yet another way. It's been debated if it's NMDA receptor antagonists or something else. I'm sure that Richardson can talk a lot about that. And then you have a purely synthetic empathogens, MDMA/ecstasy. And this guy, ethyltryptamine. One thing that is not often mentioned is that this is or was an antidepressant that was sold in, for example, France in the 1960s, 1970s. I don't think it was extensively used, but still it was on the market, and now it's a pathogen close to MDMA. For those of you who like structures, the structures up in this corner, I think, is very interesting because there is so large similarity to the endogenous compounds, those compounds that already exist in your brain. Serotonin, primarily, there is a piece of serotonin in all the classical psychedelics, phenylethylamine as well, and tryptophan being, I mean, a building stone for all the proteins in your body. It's also have quite a bit to share here, being a serotonin substructure in a sense. So one thing that is important to take from this picture is that whatever psychedelic is given to a patient is bound to have a lot of different actions. These guys don't work at 5-HT2A, they do a lot of other things. Serotonin do many, many things. And these guys will also do a lot of things inside your brain and inside the gut and everywhere where there are receptors for serotonin and these other natural endogenous compounds. So having a clean magic bullet kind of pharmaceutical drug only doing one thing in the brain based on psychedelics, I don't think so. And if we go back to this picture, these are good examples of fairly selective, but certainly not specific compounds. They do also many things, but they're useful. That's why they sell quite a lot onto the pharmaceutical market. Okay, I think that was enough of history and background. Now, a bit more about what needs to be done to understand what psychedelics do on a molecular level. Just last year was published not a crystal structure, but something called a structure at least. It was cryospectroscopy. They take very, very many pictures of a deep frozen protein in its natural state, and then they, together with computers, puzzle together the picture of exactly how the atoms are. And in this case, it's 5-HT2A and LSD. And they can see exactly what happens to the receptor in its natural state on a molecular level, which is impressive. Not very high resolution, but still very useful. So after this structure, I'm sure there are many labs in the world trying to make an improved LSD. Now, that's not easy. If you look at these two structures, I'm sure you can see the similarities. You have LSD to the left here, and you have glyceride to the right. There are some more atoms here squeezed in between, which makes both agonists. They both activate this receptor 5-HT2A at similar potencies. But whereas LSD is strongly psychedelic, Lyseride doesn't do anything. It's very inactive. So the commonly used tools in the pharmaceutical industry trying to understand on a molecular level what happens and then translate that into what will happen in animal models and in human patients. It's challenging when it comes to psychedelics. And one part of explanation for that is the receptor. 5-HT2A is one of those GPCR receptors that can activate many pathways, and it also does so, depending on exactly what you squeeze in to a receptor. Here, envisioned by this 7 transmembrane helices, you can have downstream effects with a lot of many different variations and to different extent. You can have a mixture, all these downstream cellular processes. And that is probably why, if you look up reports on how these are perceived, how the psychedelics are perceived in the human subject, even though compounds appear to be similar on a structural level and they have similar potencies, they can have widely different effects. So the pharmaceutical molecular mechanism model is a bit challenged when it comes to psychedelics. I would like to complicate things even further by showing this picture, and that is, here is another picture of this 5-HT2A, the 7 transmembrane helices for the cell membrane here. It can activate, as I mentioned on the previous slide, several different pathways, and just a little bit tweak one method group, a small change to the psychedelic compound will give this kind of effect, mostly pathway 1 activated, a little bit pathway 2. And with that just very small change, you get the opposite. So think of these compounds more like, shall we say, a piano chord. You know, you press down like 10, 20 different notes at the same time, and it sounds in a specific way. It's not a single note, it's many notes being pressed down at the same time. And that is the effect that needs to be optimized if these are to become optimized pharmaceutical drugs in the future. There is some efforts going on to try to understand what happens when, in this case, LSD enters the receptor, this 7 transmembrane helix receptor, here envisioned as a different kind of character. If you just have 5-HT2A in a mouse model, nothing happens. It doesn't activate anything. It has been shown that you need this mGlu2 receptor, which forms a heterodimer with 5-HT2A in order to get this psychedelic response. And if you take away the part which is responsible for interaction between mGlu2 and 5-HT2A, again, not psychedelic. So there is something with this heterodimer that is important. And then one could go really down into rabbit's hole, trying to understand what the structure does to proteins, receptors, and then, of course, we haven't even started on the psychology of things here. Now I'm going to jump a bit and talk about Sweden and what we can do. What we can do to try to understand this, not on a molecular level, but on a therapeutic level, is to actually work with the data we have so far, with preliminary data from early clinical studies indicating that these compounds may be quite useful in treating depression. So this is the Imperial College study that I mentioned before from 2016. These are just 12 patients. It was later extended to 20 patients. But what I think is impressive is that this is very high depressive scores from the individual patients. 1 week after psilocybin dosing, all have improved. And most of them have mild or moderate depression or even no depression. The majority have no depression 1 week after psilocybin dose. These are treatment-resistant patients that has not been anything working on. And even 3 months later, it's still a significant improvement. And 6 months later, it's very similar. More than 60% without symptoms, still in no depression mode. I think that's very impressive, and that's what we wanted to build on. So the Swedish clinical trial, I can talk more about that, but it's not really the focus of this talk today. But it's run by Johan Lundberg, psychiatrist at Karolinska, Mikael Tiger, also psychiatrist, and Maria Beckman, who is psychologist, also at Karolinska, who together evaluate psilocybin for not treatment-resistant depression, but depression, the normal major depressive disorder, or MDD as it's called. It can be the first time a patient is depressed. This is the patient group they are targeting. And it's just a single dose of psilocybin that the patients are given. And it's early days. I can't say much about the results yet, of course. We don't know who got psilocybin and who got placebo, but it's very exciting, I think. Moving on to something that is very different from my early part of the talk, and I introduce this because it's so important when we talk about molecular mechanism to understand that there is not just the receptor game being played here, but there is also on a very different level, things happening in more psychological term that can perhaps better explain how depression is really treated, because no one understands depression. No psychiatrist I've been speaking to say that they do understand depression. No psychologist either, really. It's a widely diverse disease. It's very bad to have many lost work days and enjoyment of life. I could go on. I'm no psychologist again, but I would like to point out that this is one way of explaining what happens on the psychological level when psychedelic assisted therapy is given to a patient. So all this hallucination, potential euphoria, sense of unity with others, and increased access to early memories and anxiety and fear, and potentially also ego dissolution. Very powerful effect, and to some patients, very anxiety inducing also. But it's not just anxiety, bad anxiety, but it also can be sort of a door opener to access those early memories or those potentially traumatic memories that needs to be addressed in order to actually start to work with the origin of a disease. So that's the hope, that psilocybin can catalyze transformation from a broken story, to put it that way, in the depressed patient, to be to grow into something more healthy. I like this more Jungian approach to explain it, that it's a way to lower the threshold between the conscious mind and the subconscious. And this is a researcher, Stanislav Grof, who said that it's a non-specific catalyst, an amplifier of the psyche. What is, in a practical way, really important to bring with us when we talk about this is that this is not something that will ever be given, I think, as jar of pills that the patient should take home and take when needed. This is something that requires therapist support, because the material that can come up during a session can be very challenging for a patient with depressive disorder. And having someone with expertise of handling temporary psychosis can be essential. That's a patient safety thing more than anything else. So in the future, this is most likely a clinical setting that will be relevant and nothing else. And also integration therapy, the same therapists that has been present during dosing need to work with the patient afterwards to make sure that the material uncovered in the dosing session can actually be translated into something useful in everyday life for the patient. Now that's about as psychologist I can be, so don't ask me too many questions on this, please. Still important to bring in at this slide. In the background, you see a typical dosing session at Johns Hopkins. Now, back to my home territory more. this is the best in vivo model, quantitative in vivo model to understand how animals react to psychedelics, and trying to translate the animal reaction to something that is similar to what happens in human. Quantitative, I say, because you can give these compounds to mice, and you can see approximately how much is needed in a mouse and translate that into how much is needed in a human to get a psychedelic effect. Now, you can't ask mice, is this more like psilocybin or more like 2CB? But you get a number, and the number is the number of times the mice shake their head. So, illustrated by this picture, they shake vigorously their head if they are giving a strong psychedelic compound. Well, your guess is as good as mine what this represents. Perhaps Richardson can tell more about that later. But this graph, I think, tells it all. If you have relatively impotent compound like mescaline here, and very, very potent compounds like LSD here, and the table is not possible to read, I suppose, but it says the same thing. So here you have the compounds like 2CB, sorry, it's somewhere here. Yeah, there it is. You have DOM there, you have LSD on top, and mescaline on the bottom. So that's what we have if we want to study this in animals. Not really a depression model, but still, psychedelics model. I'm not going to go into deeply in this slide because it's very medicinal chemistry specific. But what I'd like to say is that these compounds that was on the previous slide, just as names, the structure represented by the names is highly interesting to understand what can be done to tweak the molecule in order to get other compounds that are also probably active in various ways. I'd like to highlight a few. You have DMT. It's not very potent. It's supposedly endogenic, active, but we don't know exactly what it does. Richardson, again, can tell much more about that. You have psilocin. What happens to psilocybin or magic mushrooms when you eat it? Degraded in the stomach. You have this compound also, actually the most potent of all compounds, except this one in the list. And this is an glaucoma drug, an eye disease, high pressure in the eye. It's mediated by 5-HT2A receptor as well. But if you dose it so that it only gets into the eye, the idea was to treat glaucoma with that. Never reached market. I suppose it could be just dropped elsewhere and give very strong psychedelic effects. But that's just speculation on my hand. So, project outline. I'm nearing the end now of my presentation, but just wrap up to see what I am doing at Uppsala University. That is to synthesize a diverse set of psychedelics. And that's really to enable biological studies of psychedelics at Uppsala University. And also to find better synthesis methods for known psychedelics. Most psychedelics were synthesized 50, 60, 70 years ago. It's a lot that has happened with synthetic methodology since then. So we can really see room for improvement. And then number 3 here is what Richardson will talk about, how he evaluates the compounds in brains. And this is for future, looking at compounds like DMT and 5-methoxy-DMT, both with Richardson and also with MS imaging in brain slices. Not going to go through synthesis slides, but this is what I do. This is what I'm best at, really. And the improvement of psilocybin synthesis, for instance. I can just briefly mention to give you a flavor of where research is heading here. Psilocybin is relatively challenging to synthesize because it is not very stable to acid or base. It's not stable to air. You really don't want to handle it more than necessary in solution because it just grows black or blue in case of when it's in mushrooms, but it's degraded quickly. And also traditionally it has been very difficult to synthesize. So there was a publication in just less than a year ago with a kilogram scale synthesis of psilocybin, which really simplified things on how to do that by Usona Institute, an American institute. And we have been trying to reproduce that, but unfortunately, in correspondence with the authors, it was quite clear that they only managed to do this in kilogram scale one time, never being able to reproduce it. So it is still challenging to make psilocybin. And we have a few ideas on how to do it better. So that's one part of my research. Now, I'm talking a lot about Uppsala University, so I will talk about why that is. Narcotics banned by the UN Treaty in 1971 of psychotropics is in Sweden implemented so that you basically can't have it, certainly cannot use it, and everything is very strictly regulated, except in the context of research. So this is a cutout of a Swedish law. Narcotics may be held by a scientific institution like Uppsala University. Now, the implementation of that is that if I produce a psychedelic compound at Uppsala University, I can synthesize it, I can transfer it to Richardson, still at Uppsala University, who do scientific studies with it, but it may never leave the university. It may not even go to collaboration partners at Karolinska Institute. Because of the interpretation of the UN treaty is that you need to basically have permits for every step of the way. And it's quite expensive, takes time and a lot of bureaucracy, because this needs to be approved by the highest level of the university before it can leave Uppsala and enter Karolinska. So it's actually easier to make these compounds ourselves and study them at Uppsala University. It's not very effective, but it works. So to summarize, we see a renaissance of psychedelic research, especially in clinics, but there is a lot happening in non-clinical studies and design of new psychedelics and the preclinical studies of those as well. And again, reiteration, these are not pharmaceutical drugs really. It's more catalyst for therapy. And we don't really understand how they work, but we need to start to study that in some way. And there's so many ways to do that, but I feel that we have a good chance of doing that between me and Richardson and a few other researchers at the Uppsala University. We need to improve synthesis of known psychedelics to make them more accessible. And the long-term goal is to make rational drug development. That is to make compounds that are with more desired effects and less of nausea, the really difficult side effects that psychedelics sometimes comes with as well. So improving those that are the psychedelics compounds. So that is what I had, and I'd like to transfer now to Richardson. Is that what you would like to do also, Marcus, that we don't really have a question session here, but we move directly to Richardson and take Q&A afterwards?
Yeah, that's what I thought as well. We can just have a question session at the end. So
yeah.
Thank you very much, Ulf. It was a really interesting talk you had. And I will give it now over to Richardson, who will take us more into the the mice dreams, I guess. Yes, Richardson, can you share your screen?
Yeah, just trying to share the screen here because
perfect.
Okay, because I came back to my origins since my PhD, like to do patch clamp and so on. So I always had this, boring traces. There's no colors there, but it's just like it's something very plain. And but then I learned with Ulf that plain may be good, because somehow when he said that chemical structure, that I think like, oh man, it's like, how can that be like, it's like a language and like a character. Well, that was very inspiring. So I think now I'm gonna think about my boring traces as a character inspiring. And also I apologize for the quality of the slides, because I had my computer with all my data, the computer burned off, and then it's like everything is closed because they're locked down here. I'm trying to buy Word, it's impossible. And then I'm trying to download Word, and I have a computer in Swedish that doesn't allow. And then I arrive home, my kids are depressed. My girlfriend ran away with my cat. So actually I'm trying, I'm here in her house trying to, bring back at least the cat. So I'm really sorry about the analysis I did. And then my computer, yeah, but it's here. You're gonna know what you're gonna see what I want to show. And at this time, I had before I talked to you guys with about depression and the depression models and so on. Here it's gonna be plain cell channel physiology. So we don't have to elaborate about how a mouse is depressed, like the mouse that arrives home, beat up the wife and so on, or how a mouse is hallucinating or whatever. So it's just pure cell recording. And then I'm not going to talk about serotonin, because I think this data, it's actually something else. And so what happened is, like, when I gave a talk to you guys, I think it was the first semester, I had the immense pleasure to meet Ulf. And I know he said that we're not doing breakthrough science. I think, like, if you meet someone and then a few weeks later, he synthesized compounds that you just hear, in fiction, or like if you order from Sigma, it takes 1 year, and then you get these compounds in the, in a way, like I thought it was fun, because like we were in a restaurant and say, oh, I synthesized the compounds. It's like, you're buying drugs inside the university. So, the whole thing was fun. And then it's like, this I think we produced a lot of data in less than 2 months. So for me, it's remarkable. I think it's, you, at least for Brazilian standards, you say, oh, let's collaborate. And then, like, people already found out how the brain works and so on. There's nothing to talk about. So this was super fast, and was thanks to you guys. So what I did, Ulf gave me 3 things. I had worked before with 5-mel DMT, this frog stuff. And then I had like one study that will show that it doubled the neurogenesis. So you give a single dose of 5-mel DMT in an anesthetized animal, and then we check neurogenesis, because for people that doesn't know, the people, we tend to think that the brain does not create new cells, right? The adult brain, no, but it's not true. You have at least 2 sites in which neurogenesis it's a phenomenon that's actually it probably has some cognitive function. And in one of them is this place in the hippocampus that's called the dentate gyres. So the dentate gyres is just a little curve in the hippocampus. So this would be like the hippocampus is like a sausage. Then you have the upper part that is a happy hippocampus, and then you have the lower part that is a sad hippocampus. When I say happy and sad, one is, at least in rodents, like one is involved in, like running and, things that mice do for fun. And then the other one is it's involved in anxiety or depression or, even food intake. So in this place, in the dentate gyres, where is here, it's one site that you have neurogenesis. And then there is a group of people in psychiatry that thinks, there's theory that like neurogenesis, adult neurogenesis, is part of the antidepressant treatment. So it's like, if antidepressant works when you do the, what's the word that they use? Impregnation. At least here, the psychiatrists know that, oh, you have to wait for the antidepressant to impregnate. And that coincides with an increased neurogenesis, right? And then they think that this neurogenesis phenomenon that actually participate in depression. And then my student, Rafael, I think he's even here, he actually did this study and showed that, not only the neurogenesis increase, but also the new neurons they become neurons faster. So, I mean, when a neuron, the neuron is not born a neuron, like first they have to create the dendrites and then get the channels and start firing and then connect. And then you have the neurons that fire together, wire together and so on. And then they participate in this with other friends and they talk to each other and then the brain works. So that was my first contact with this. And then after we had a study with electrophysiology, I haven't put this here just because there's nothing, it's not related really to the thing. So we did like local field potential, and then we put the mice in open field, and then also this elevated plasmates. So basically what they think is that mice that goes in the open, so the elevated plasmates is a cross in which you have two arms that are closed and the mouse is safe, and they have two arms that are open that is, you know, for the epistemology of a mouse, it's like a 30 floor building. So you know, if they think that if the mouse is depressed, the mouse stay inside the closed doors. I think it's just, you know, the mouse is just like, you know, safe, or just like not stupid to fall out. But anyway, so the people believe that, and I'm not here to judge behavioral models. As I said, it's like I did my PhD in patch clumping, single channels. I incidentally moved to behavior, and I think sometimes internally, I mean, now it's not internally because I'm actually externalizing it, but sometimes I think those assumptions are quite fun. You know, it's I really like, I think what is a depressed mouse or an anxious mouse or a brave mouse, you know, like. But anyway, so people believe that, and that's what we have. And so we found that like if you give a single dose again of 5 ml DMT, mice get courageous. And then also if you have, we study tinnitus. So tinnitus generate anxiety in animals. And this, we have a very nice model of tinnitus that you can actually show that the mouse is hearing something that's not there. So a phantom sound. And then when they hear these phantom sounds for the first time, they get very anxious, they freeze. But if you pre-treat the animal with 5 ml DMT, a single dose for weeks, they are, you know, they probably still have, no, they do have the tinnitus, but they're, you know, they're not anxious anymore. And that's, for me, was amazing because, you know, it's like, I always thought that, you know, like psychedelics was this study for, you know, hippie scientists that, you know, give good morning to the sun and hug trees and so on. But no, it's not like, it's mice, you know, it's like mice is not in the hippie movement, or it's LFP. So LFP, again, LFP is not something that, you know, you came out of your mind after you drink like a mushroom tea. So that was amazing. It's something that, like, I think I'm about to change completely the way I want to do my research. I'm still not a hippie. So I think it's like psychedelic research need people like me that doesn't believe in this. And like channels, and like, you know, go to the deep part instead of, you know, saying, oh, I'm going to see God or whatever. So what I did, we have several animals that we can actually mark single neurons. So we have an animal that you can find. So the hippocampus has, I think I have a slide for that. So I just show here the dorsal and the ventral. The hippocampus has several types of neurons. So actually several types of interneurons. You have like a few types of pyramidal cells that is the main cell that compose most of the cells that are the output, or the cells that are excitatory. But, you know, like, to make the circuit fun, you have all these different types of interneurons that do different things. So we have a model for an animal. When I say that we have an animal that we can find these neurons, basically it's a transgenic mouse that when you cross with a reporter, so we cross with a, you know, like we have a tomato or GFP or whatever, so fluorescent protein, you can actually find it when you slice. So I should have put like, because I didn't know my audience, but I should have put some pictures of what is slice and how we get this brain slices. But basically it's like you cut a piece of brain alive. I mean, alive, yeah, it's like the cells are alive, right? And then you put this in under the microscope, and then you have all the cells, but then you can't really differentiate them. But then we have, you know, we can have an animal that have this OLM cell that is fluorescent. I also have one that has another very important neuron that's called the basket cell, and it should be here somewhere. And then pyramidal cell. So what I did was, so the hippocampus had these three major structures. So back here, it has the dentate gyres. It has this part here that's called CA3. And then this part here that's called CA1. And this is called the trisynaptic pathway. So I look at the dorsal and the ventral hippocampus in pyramidal cells and in granule cells of the dentate gyres, in CA1, CA3. So it's like two types of interneurons in CA1 and CA3. the pyramidal cell in C1 and C3, and then the granule cells in the dentate jars. And these granule cells, the dentate jars, they are the cells that are born when you have adult neurogenesis. Yeah, so here would be the dentate jars. So the dentate jar is also a very important structure, and that's something I want to revisit, because once upon a time, I was studying, no, somebody in the lab was doing epilepsy model. And then because I had the ethics permit for two, I just say, oh, maybe one DMT does show the epileptic model. So I have one recording that was really amazing, but as it was one, but it's something I want to revisit. And then the dentate jars, it gives epilepsy. It's important in epilepsy because it forms these new cells, and then the new cells have this giant synapse. So it's a synapse that if the granule cell fire, the pyramidal cell in C3 also fire. So let's say if you have this synapse fucked up, then what you have is just like you're gonna have this massive activity. So it's like the dentate jar is the right place for you to create epileptogenesis, to create epileptic seizures. So yeah, this is what people study. It's important. And then there, like people, I mean, there are several theories why you have these new cells. I'm not going to go into detail because I don't believe any of them. So here it's like, as I said, the happy and the sad hippocampus. You have, or the happy hippocampus is connected to the septum, and the, I don't know what it is. But then the ventral hippocampus, that's what we study the most, is connected to the structures that are related to, to mood disorders and to anxiety and so on. So like the prefrontal cortex, the amygdala, hypothalamus, and so on. Then, this is the part that I think, I don't think Ulf likes it, because all the time that I talk about sigma 1, he kind of like talk about something else. But so it's like, it's like when you do patch clamp, like let's say, because people have some understanding of electrophysiology, and it's this kind of like, that you can actually show everything, for example, but there's some things you can't show. One thing that you cannot show is activity of metabotropic receptors. I mean, people have this tendency to do things that they believe that's right, but no, when you put an electrode inside a cell, a patch clamp electrode, the electrode is huge, the electrode carries fluid to emulate what you have inside the cell, but the electrode does not have G proteins. The electrode does not have, skeleton proteins. The electrode doesn't have none of this. And then when you put the electrode, you actually, it's like it's not the uncertainty principle, but it's kind of, you wash out what the cell has inside. So you cannot record things like 5-HT2A. I saw many papers that they see something that, it's like, it's kind of consequence of the 5-HT2A activation. But for patch clamp in a single cell, 5-HT2, serotonin receptor, except the 5-HT3, right? Dopamine and all that does not open a channel, it's bullshit. So what I think I'm looking here, it's a postsynaptic response that's caused just by the DMT. It's not like something that is activating serotonin receptor or whatever. I'll show you like something, and I feel like I need to figure out like what kind of experience I need to show. But here, it's something that does not look to me 5-HT2A linked effect. So this sigma-1 receptor is a receptor that, even now they found that the COVID, it actually used a bit of sigma-1 receptor. And it basically, I don't know what it does, but one thing that I know it does, it control currents. So I mean, control currents, let's say, the action potential starts when sodium enters the cell, and then it depolarizes the cell, and then potassium enters, then the cell repolarizes, so on. So let's say that if you have another receptor that increase the time that the sodium takes to open, so it's like it delays the opening, then what means is like a lot of cells are going to actually not have any activity, because if you delay the time that the action potential is starting, the sodium is entering the cell, you could have potassium currents being activated before the sodium enters. So you have the cell kills the activity before it happens. But let's say if you fasten the time, then again, a cell that just fire one action potential per, memory of your grandmother, gonna fire 10. So, or then it's like this is, it's a very, the net effect of you to delaying currents or decreasing currents or increasing time it's for at least for sodium and potassium, it's more important than, for example, increasing amplitude. For example, like one in epilepsy, you have one thing that people, it's an old medicine, it's called, I don't know if Tegretol is the carbamazepine, yeah. So the carbamazepine just changed the time that the action potential takes you close. And then this is enough for you to stop a seizure, right? Diazepam just increase a little bit the decay of GABA, of the chloride current in GABA. I mean, this is enough to stop a epileptic crisis. So, I mean, all these small changes in the cells change a lot, like the net effect if you check all of them. So what the sigma-1 receptor does, it basically changes a lot of currents. It changes a lot of potassium currents. Some go up, some go down. It increases calcium currents, and then also modulates sodium currents. And then in 2009, there was this paper, the hallucinogen DMT is an endogenous sigma-1 receptor regulator. The dose is a bit higher than what we're using here, but I think the result is kind of, I don't know, I have to think about it, but I can't think of this as a 5-HT2A. Okay, so this is an example of a bad paper in which they show you put serotonin and then you have this increase in current. And I mean, this is kind of like a lot of things I mean, this does not say what this evolves. Like the same cell, if you record half an hour after, the response is going to be different, because what you have when you patch a cell, as I said, you wash out all the proteins that make those currents to be alive, and then also you change some of them. You know, like maybe, oh, the receptor now it's an inhibitory receptor, and then the protein that's gonna sign to a channel, now it goes inside your pipe, so that's gone. And then probably that's what most happen, but it's like people try to do it, and that would be the kind of effect you would expect. And then I have a effect very similar to this, and I'm gonna explain to you why I don't think it's actually serotonin related. In the hippocampus, like most of the 5-HT2A, it's actually in the interneurons. So pyramidal cells don't have much of it. So what I'm doing here, we're actually modulating the pyramidal cell activity, and then I'm going to show you that this effect in vivo, it exists in another set of data that's not related to what I'm doing with Wolf. It's just some new thing, but I'm so happy to work with Wolf now that I think I'm just going to dump my other collaborators in. Anyway, so what I did is like, if you statistically, it was a lot of things. So we have 3 drugs, thankfully, because I didn't give him time to synthesize more, because he sent a list of 10, and I have to explain to him, like, if I do 10 with like 10 different types of cells, it gets, these things grow exponentially. And I'm 45 years old, so I want to finish before I get a heart attack. Or so it's we use these 3 things. So DMT, DOM, 2CB. And I tried in the ventral and dorsal hippocampus, the ventral and dorsal hippocampus, so like the dentate gyres of ventral and dorsal, and it's here one of pyramidal cells, basket cells, and OLM neurons. And to my surprise, none of the compounds except DMT had any effect. So this is an example of CO1. It's like all the neurons I tried, and this is with all the 3 compounds. And I mean, it looks like the current is moving, but this is just like because it's a long recording, and then because we don't have a low pass filter, this is like just the drift from the silver in the pipette and so on. So this is nothing, and you can see by the amount of current here. And then if you see those little spikes, except this is noise, but those little spikes here, they are, so this is the base recording, the current base, and then those little spikes are presynaptic events. So these are because of, since the time of Hodgkin-Huxley, the things that go down, that are negative, they're excitatory. So because what we are reading here is the amount of current that the amplifier needs to give to the cell for the cell to not change voltage. So those things here are EPSCs. So what you have here, it's like you don't see, I apply DMT slowly, and probably like after 50, 60 seconds, it reaches the bath, and then you don't see any change, not in the basal current, and they also doesn't see any change in those EPSCs. And this is the same for DMT, for DOM, for 2CB, and for all cells that we try and say one, dorsal and ventral, and then also on the ventral dentate gyres. But then you have the, how is that called? The book is the holy molecule. So the DMT, for some reason, it gives a very strong effect in the dorsal dentate gyres. And here is the control, right? And this is the, when you apply DMT, it's a 0.3 nanomolar. And I mean, all this data I'm showing you is statistically significant. So it's just, as I said, I apologize because I have to, I talked about this already. But it's like, you can see this basal increase, and then it washed out after I take out. And this washout is like, it goes basally, just that I had to crop here. Because what I want to show to you is not only this, but you see, here's APSCs. Here you see a big one, but then you have this burst here. And what I'm saying is that, remember, this is slice. So it's slice, like the most of the inputs to the dentate gyres, they're severe, but you just have the, the terminals stay there for hours. And then when I look at those, I see, for example, if I get a small one from before the DMT, and I check with the bigger one from after the DMT, they look the same. And there are several possibilities. They look the same as time. Not that they're bigger, but they have the same time, and they have the same decay. So that normally when you see a current, you measure two things. You measure the rise time, that is the time that the channel opens, and then the channels close, and then you measure the decay. And this is too slow to be AMPA. So the only thing that's left there is an MDA. I'm sure that when we're going to publish, some reviewer is just going to ask, oh, but have you blocked an MDA? You say, no, there's just two things in the words. Just like if you find something else, you're like, it's a Jesus or something. But yeah, they will ask. So I will block it to show that MDA, because I mean, I think this is, standards in patch clamp experiments. But it's just like, it's this, the current is just amplified. And being amplified is like, you cannot, like, if you have a receptor, the receptor has an amount of, if you have a synapse, you have the boutons and then you have the receptors. You cannot like just double the receptors because you have a drug on it. So this takes time. When the thing just grows like this, I think the easiest explanation is that this is not a presynaptic phenomenon. It's not because you're having more NMDA, but because something in the dendrite is amplifying this. So how you amplify something like this? For example, the dendrite has several channels. If the channels are open, they are leaking, right? So if you have a current, a synaptic current that arrives there, and the channels are open, then this current leaks, and then it doesn't get to the soma. But now if you close it, so because you remember Ohm's law, you have a voltage equal to current times resistance. So if you increase resistance, so remember that all these voltage gated channels, like for you to have an action potential, it's voltage based. So it's like you have to reach a threshold of voltage, not current. So if voltage is equal to current versus resistance, if you double the resistance by closing channels, for example, you double the voltage without changing the current. So, I mean, that's a very easy way for you to have plasticity, for example. But I mean, this needs some more investigation. But then now we actually have to, if Ulf agrees, we have to actually to nail down to the DMT if we want to go to this direction. Otherwise, I mean, I'm your slave. If you tell me to do whatever, I dump all the things and we do whatever. We can do the crazy depressed mouse. But I think now to see which currents are actually being activated if there is a current that's amplifying, that's the opposite thing. So it's like the channel, the synaptics go to a dendrite, the dendrite is active, it has sodium channels, so the sodium channels get active and then it makes the synapse stronger. And this is extremely important. This guy here, so this is a synaptic event. This guy is probably not gonna pass any information, but it will pass on, always. If you have a large current like this, the action potential in the postsynaptic cell always going to happen. So I mean, this is a as I said, like in the net effect, it's very important. So I mean, I think this is the main finding with the stuff I've been doing with Ulf. And I have to say, this was done in December. And in December, you know, you have Christmas and New Year's, and so it's like, if it was a normal month, we probably would have a paper now. And I again have to say that I'm very happy to work with him. With you, now you're here. And the other thing I did was, so I said dorsal hippocampus, right? And then we did a gene study. This I have to thank Thiago. It's like it's a colleague of mine that did. I forgot to put his name here. It's Thiago Moulin. Moulin, it's a French name. Sorry, I have to write here because it's awful. So he's also in Uppsala with Helgi. Okay. So what you have is like in the, if you see, it's the only place where you have sigma receptors in a significant level is in the dorsal dentate gyres. But still, yeah, I know that people don't like the sigma one. It's, yeah. So the extra part is like, this is some data that I collect myself. So it's just like, there was this talk of David Nutt, and then I got excited about it because he said, I asked him in the end, like, which cells do you think when you give LSD or psilocybin, which cells you think are activated? And I think like, you know, because I mean, people that do clinics, I mean, it's like, my father is a neurologist, for example. So if I ask him what is a sodium channel, he has no idea. It's like, you know, and then when they say, oh, he said, oh, it could be inhibitory neurons, and then he said it'd be chandelier cells. And I think people like that, especially fMRI people, because it's a nice name. It's easy to remember. But it's like it's a very broad name. And then what I think is like the idea that you have inhibitory cells activating your brain is crazy, because it's like they're gonna see the brain activity dies when you give DMT, but the mouse is still crazy there. So maybe they might see God too. But here I'm gonna use another technique. It's something we're doing pretty good in the lab. So basically we implant, the animals have a fluorescent marker, fluorescent calcium indicator, so that we can actually see the brain activity. And then I apply DMT and I record for you know, several minutes. And it's like, I cannot record for very long because it's like, it's terabytes of data when you record like that. But then it's like, this is just an example. When you apply DMT, so all these color traces here, it's a cell that is firing. And then you have this guy here that's firing before, and then in the hippocampus, you know that these guys that fire, you know, repeatedly are inhibitory neurons. They are basket cells because they're called fast spike neurons. So it's like, that's what they do. And then when you look at it, you have activity here. It's like the contrast is not nice here, but you have a lot of activity in the beginning, but then these guys start firing like crazy. And then even they die out, because yeah, it's what inhibition does. If you inhibit too much, they inhibit themselves. And you can see here. So it's like, this would be this guy firing before. No, this is like the time here. And then this is the inhibitory interneuron. And this is the pyramidal cell in black. And then you go, and then for longer you wait, the activity stops. And I mean, I get amazed that, you know, like, if you look at what DMT, you know, DMT of psilocybin people do, it's like the basic part is not there. I don't know, maybe I'm looking the wrong PubMed, but there is a lack of basic studies of like cell level or things like this. And then you see, it's like, it's exactly what he said. It's not the chandelier cells. I would like to be, because it's really, chandelier looks prettier than basket, but it's there. So it's like the cell die out. And then I repeat these experiments with a marker for just inhibitory cells, and it's very evident. The excitatory cells, they seem to not respond, at least not initially. And if you, let's say, if you apply GABA, for example, I mean, like if you apply GABA in the brain, you don't trip out, or you just sleep or die, you know, like it's this is like the activity dies out. And if you look at the LFP, so the local field potential, it's exactly the same. So this would be what the mouse. So the mouse was walking in a field, in an open field, and this is like the most prominent rhythm it has in the hippocampus, is the theta. We apply DMT, it dies out. And we have a lot of like this. We have a very huge N, and it's amazing. It's like nothing is there. So what is there? So it's I think, acutely, there's a lot to do with this that has to be answered. The only thing I found is this very, very little gamma. And as it was done here, so it's between 50 and 60 hertz, so it's not actually electricity. So the only thing is this little gamma. So everything else is sleeping. So yeah, I think that's something that people should explore, or we should explore. Okay, so I don't know if I took too long or too short, because as I said, I'm locked down. I completely lost the idea of time. And the conclusion is, for the PET study, is that like the DMT postsynaptically is acting only in the ventral and dorsal. Man, come on, wait. In the dorsal DG. So I kind of have some ideas to explore if this is sigma 1 or serotonin. I don't think we can actually go many. I think my idea was to branch this here now and just finish the story to see. And I really like it. I would be happy to show that it's not sigma 1, just to not upset tools. But I don't know, man. I think it looks very much that it can be explained by serotonin. And yeah, so thank you guys again to invite me. And yeah, all the time you need, I'm here. And yeah, now it would be the questions, right?
Before the questions, just let me add one conclusion there, Richardson, and thank you for the presentation. This was really fascinating for me as well. Since you have been in Brazil, we haven't met as much as I would have liked to discuss these results. But one conclusion that's important, sigma has an Ki value of something like 15-20 nanomolar for DMT, but you observe significant effects at 0.3 nanomolar, right? So there is something that is not quite right with interpretation that it's only sigma 1 that stands for the activity you measure. And sigma is a complicated ion channel as well, a receptor. So there may be things that we really could uncover here that are quite exciting.
I mean, the other option would be some direct effect in some other stuff, right? So it'd be...
Yes.
I tried the most. What I did, I didn't put the data because I try, the things that I know that, are also can be modulated by CMP or things like that, by ligand. It would be like IH, that's the current that it's important for keeping the dendrite tight. And I try other potassium currents that are affected by, muscarine and things like that. And I haven't seen anything. But again, could be, postsynaptic, but for me, it's hard to think about like how it would be postsynaptic. Like you recruit more vesicles, or I could think,
Richardson, we should postpone that discussion between you and me and hear what the audience has to say. Sorry. Because probably a different interest than you and I. I don't know.
Yeah, but